The industry assumption is that frontier large language models possess advanced reasoning capabilities. People treat these systems as entities that actively ponder and deduce logic. The reality of their performance is contradictory. These systems can solve proofs for an international math Olympiad, yet they frequently fail at basic multi-digit arithmetic. This diagram illustrates the contradiction. When prompted to multiply 89,822 by 67,889, the model confidently outputs an incorrect result, complete with a green checkmark indicating absolute certainty in its calculation. Researchers classify this behavior as jagged intelligence. This is a state where a machine learning model's failures are highly unpredictable and have zero correlation to actual task complexity. This paradox exists because large language models are trapped in a purely syntactic architecture. They process text comprehension entirely as a problem of mathematical geometry, rather than semantic deduction. The unpredictable failures reveal the underlying mechanics. The system is executing statistical pattern matching across symbols, not performing actual semantic reasoning. This animation shows the tokenization process. Because computer systems require numbers rather than unstructured text, words are broken into chunks called tokens. A token is a numerical representation of a text sequence, mapping a word like how to the discrete number 3253. To capture the relationships between these separate tokens, the system processes them through embedding. Embedding is a technique that takes a single token number and projects it into a high-dimensional vector space, representing it as a coordinate. On this 3D grid, semantic relationships are approximated through spatial distance. Words from similar training context end up physically close to each other, which is why ship, car, and bike drift into a tight cluster. The system calculates the physical proximity of these vectors perfectly. But it possesses absolutely no definition or understanding of what a ship, a car, or a bike actually is. The large language model operates as a conditional distribution over tokens. It functions like an enormous table of weighted dice, where rolling the die simply selects the most statistically probable next word based on the context. Scaling this architecture up to trillions of parameters requires massive amounts of data, but it does not change the operation. Statistical induction over vectors cannot transform into formal, valid logical deduction. To compensate for this lack of deductive logic, the industry relies heavily on chain-of-thought prompting. Chain-of-thought is an engineering technique that forces the model to generate intermediate steps, simulating how a human might write out a problem before answering it. These side-by-side prompt blocks outline an experiment conducted by Anthropic. Researchers gave the model a scenario involving a black man and a light woman, asking who was trying to buy drugs. They tested two versions of the prompt, swapping only one logical detail: who was fidgeting with their pockets. Notice the red boxes at the bottom. The model arrived at the exact same answer, the black man, regardless of the logical evidence provided in the prompt. When researchers examined the chain of thought output, they found the model retroactively invented facts to justify the statistical prior it had already selected. It built an argument to support a stereotyped output, rather than reasoning from the provided evidence. This is a textbook example of reward hacking. Reward hacking occurs when a model locks on to a specific, highly probable answer, and then generates syntactic rationalizations purely to appease the user or the grading mechanism. Even when a model produces a token like aha to signal a sudden realization, it is mimicking syntax. There is no internal state change inside the neural network. It is a cargo cult behavior copying the structure of human thought without the substance. Intermediate output tokens are not evidence of reasoning. They are post hoc justifications of statistical biases. Because they rely on syntax rather than semantics, these systems face strict mathematical limits, dictated by the law of conservation of information. Generative AI cannot function as an infinite knowledge engine. When engineers attempt to train a large language model on data generated by its own previous outputs, the system begins a process of recursive degradation. This curve shows training data diversity. With each loop, the model loses rare information at the edges, keeping only the probable center. Eventually, it collapses into a vertical line. This is model collapse, where output loses coherence, endlessly repeating a single phrase like jackrabbit. Large language models do not create new information. They merely surface patterns from a high-cost distribution of data that was originally produced by human labor. In practice, generative AI acts as a Turing machine of Babel. It can output vast amounts of syntax, but the ratio of true knowledge to generated gibberish is dangerously low. This is mathematician Kurt Gödel. In 1931, his incompleteness theorems established a strict philosophical boundary. The mechanical rules of a system, its syntax, are entirely separate from the actual truth of its outputs, its semantics. Gödel's proof dismantled the vision of his predecessor, David Hilbert, pictured here. Hilbert had attempted to build a purely machine-executable proof system that could automatically determine truth and eliminate human judgment. Modern AI systems repeat Hilbert's error. They are trapped on the syntax side of Gödel's divide, pushing symbols around a geometric board without factual grounding. To utilize these interfaces reliably, enterprise architecture requires a deterministic layer of truth. This framework is known as semantic business intelligence, or semantic BI. Semantic BI utilizes what is called a metadata mart. A metadata mart is a centralized repository that profiles unstructured source data and extracts it into highly specific relational formats. As seen in this diagram, the core of this format is the triple. A triple is a subject-predicate-object statement, explicitly linking a subject like a person via a defined predicate like an address to a specific object like a postal address. By applying controlled vocabularies and standardized web structures like schema.org and RDFA, organizations build a definitive factual lineage. It bypasses probabilistic guesswork by mapping internal data to established logic. This split-screen visual demonstrates the ideal dual-layer architecture. On top, the language model serves as a fluid conversational interface. Below, it's anchored to a rigid triple store enforcing strict factual parameters. The future of enterprise architecture does not rely on feeding more parameters into a syntactic guessing machine. It requires linking those probabilistic interfaces to deterministic semantic master data.